Good day, I'm Dr. T and welcome to my office. So today I'd like to talk about one of the classic ways, or I should say a family of classic ways of identifying your compounds, and that is known as spectrometry. So when doing spectrometry, what you're looking at is how does your chemical, respond to light. And there's actually quite a few different ways of doing this, mostly depending on what type of light you use and what that's going to tell you about your material. So the first type of light I'd like to talk about is visible light. This actually tells you the least. Most organic molecules are going to be either clear liquids or white powders, and yeah, that doesn't tell you much about them. If you jump into the ultraviolet or UV into the spectrum, that is going to start telling you if you have things like aromatic rings and certain types of double bonds, specifically those that you'd find in carbonyls. But it doesn't actually tell you a lot about them. So unless you've got some long conjugated systems, it's not going to be the most helpful in organic chemistry. Now, in inorganic chemistry, when you're talking about metals, that's a different story. A lot of metals will interact with the visible spectrum and do some really interesting things. But organic molecules, not so much. The nice part is, though, it's usually very nice and quantitative. So if you can lock onto something, if it does have a chromophore for the visible or ultraviolet part of the spectrum, aka a part of the molecule that absorbs light in one of those parts of the spectrum, then you can get a very accurate quantity of how much material you have using Beer's law, and that's going to be absorption, which is going to be a logarithmic function of how much light doesn't make it through your sample, is going to equal the concentration of your sample, how much that particular sample is able of absorbing that particular wavelength. That's what we call the extinction coefficient, and then how long it traveled, or what we call path length. So concentration times extinction coefficient times path length. And that's going to give you the ability to figure out concentration. So it's a great technique for that. We use that a lot when we can, but for a lot of organic molecules, they don't really have a good chromophore on them. So no chromophore, no visible spectrometry. Really, no chromophore, no spectrometry of the type that you're lacking chromophore for. Now, while UV vis doesn't typically work for most organic molecules, what does work well is infrared. And the chromophore for infrared typically are the actual bonds within the molecule. See, bonds aren't, fixed. They're not just sitting out there like rigid. They flex, they wiggle, they spin, they come in and out, up and down. They do all kinds of weird things. And quite often in classes we'll do the IR dance where we, do the different modes. That's all I'm doing, but it's still a great way of highlighting that these molecules aren't just sitting there doing nothing. And those flexings, stretchings, etc., those are going to have energies that correspond to infrared spectra. So if you've got your infrared spectra, you've got your photons, and if a photon is able to interact with a bond and cause it to start stretching more or flexing or doing other things, then it's going to be absorbed. And thus, hey, you can see what types of bonds you have because each different type of bond is going to respond somewhat differently. The infrared spectra is typically broken into two regions. One region you're going to have ones that are characteristics of certain types of bonds. So you're going to be able to look at those, see, does it absorb here? Well, in that case, it's telling me I have an OH bond. If it doesn't, that's telling me I don't have an OH bond. The other part of the spectrum is known as the fingerprint region. In this case, those energies correspond to far more complicated pairings. So it's not just one bond doing this, but it might be, this kind of thing. So really complicated vibrations and stretching patterns. So for those, you can't parse out what each peak means because it's too complicated of a mess. But it will create a unique pattern very much like a fingerprint does. So, the way you match fingerprints is you actually match them. You don't try and interpret, well, okay, this swirl means they're this tall. No, it's just, okay, these swirls all line up. And so for this part of the spectrum, we actually call it the fingerprint region. And this allows us to positively identify a molecule by lining up its fingerprint region with the region of an identical molecule, or one we know what it is, and if they match, we know they're the same, and if they don't, we know they're not. So this gives us a great way of identifying what our compound is. Okay, so we talked about ultraviolet and visible, which typically get clumped together, is UV vis spectrometry. The same instrument works great for both. Infrared spectrometry, which usually isn't very good for quantitative work. Beer's law still applies, but it just doesn't work as well. There is work on doing quantitative, though, for that, but it just doesn't work as well. Then what we can do is jump into, and we can actually go all the way to radio waves. And so this is known as nuclear magnetic resonance spectrometry, or NMR. This one is actually looking at the magnetic field involved with the nucleus. So some nucleuses will have a nice little magnetic field to them because they will actually have a bit of a spin to them. So if you take the nucleus of an atom that has a nice magnetic field to it, and hydrogen has one of the nicest ones. So a nice H1, you know, the one proton with an electron buzzing around it, you know, the simplest of all atoms, has a very nice magnetic field to it. So if you put that into an external magnetic field, basically around a gigantic magnet, and if you're thinking giant magnet, that sounds familiar, like an MRI? Yes, exactly like an MRI. MRIs really should be called nuclear magnetic resonance imaging, but the nuclear got dropped for PR reasons. They're doing the exact same thing, just they have a three-dimensional resolution where typical nuclear magnetic resonance spectrometers don't. They have better wavelength resolution, but not as good. They have no three-dimensional resolution. Okay, so in both cases, you put a big magnetic field around it. The little magnetic field of the nucleus lines up with the big magnetic field of your big magnet. And these are ludicrously large magnets, to the point where you have to have safety considerations because they're so powerful. And then you hit a radio pulse into it, and that's going to disrupt the magnetic fields of your atoms. And then as they restore back and line up their magnetic fields with the larger outside magnetic field, they'll give off radio frequencies. So typically speaking, you send in just like all the radio frequencies, and then you listen back for which ones come back. And that way it tells you about the atoms. Now it's like, well, wouldn't they all have the same frequency if they're all hydrogen? But that's where the power of NMR comes in. Because there's electrons buzzing around, and electrons have their own tiny little magnetic fields too. Any moving charged thing will. The electronic environment will determine exactly what frequency comes off because it will have a slight impact on the magnetic field. Now, this means if I've got a carbon bonded to an oxygen, that oxygen is going to start pulling some of those electrons away from it, and it's going to have a slightly different magnetic field for the carbon, because some isotopes of carbon can do this, but also any hydrogens attached to that carbon. So you're going to have this pulling factor. So this is going to allow me to determine what types of bonds I have, and I can actually start determining a couple of bonds down the pathway as to which ones I have. And this will allow us to actually build the molecule together. So like, okay, I know I have a CH2 at some place. I know I have a CH3. Oh, look, I have a C double bond O next to that CH2. Okay, so this gives me an idea of how to build my molecule together. Gives us a ton of information. We can do this with hydrogen very, very easily. We can do this with carbon, only one isotope, and it's not a particularly common isotope. So it's not so great with carbon. There's a couple other atoms, but you have to have really specialized instruments to do those atoms because they give even weaker signals. But yeah, this is a great technique, very, very powerful, although it does require very large magnets, which means expensive instruments. So, you know, it's an option, and most schools will have at least a basic NMR on hand. But other techniques are used because those things are expensive, and, you know, it takes a little while to do this. The last technique, spectrometry, I'd like to talk about is mass spectrometry. And this is actually a little bit of a different technique. It's not actually involving light. Instead, it is taking the material and separating it out into a spectrum, but not of light, but of mass, which is a really weird way to say this. So what we're doing is we're taking our molecules, we're separating them, getting them all by themselves. So this is going to take place in a very hard vacuum. And we're going to strip them of at least one electron. They have to be charged. Ideally, we want a single positive charge on our molecule. And then we are going to hurl it down our mass analyzer. And what our mass analyzer is going to do is one of a couple of different ways. And there's several approaches here. It's going to separate the atoms out based on mass. And that way, once they hit the end where there's a detector, which is something to register, oh, there's an atom. Once it hits the detector, by separating them out by mass, we'll know how massive they are. We'll know the atomic weight of the atom or the molecular weight of the molecule that we've then hurled down there. Specifically, we actually know the mass to charge ratio. So if we accidentally take off 2 electrons, then it'll look like it's half as big. Now, with this, we've got a couple of approaches that we can use this information for. For starters, we got the molecular weight. That alone can be profoundly helpful. Simply knowing that, hey, does it match what I want? No? Well, I guess not. Or, yes, it does. Hey, this is probably it. Alternatively, we can actually get a molecular formula. And you're of course thinking, yeah, you could add up the atomic weights, but wait a minute. Couldn't I have, say, 16 hydrogens or an oxygen? Wouldn't they weigh the same? Well, they would weigh almost the same. And to a couple of decimal places, they would weigh the same. But if you have several decimal places worth of precision, what we call high-resolution mass spectrometry, then, hey, you could tell the difference between 16 hydrogens and 1 oxygen. It just needs lots of mass resolution. Those instruments, by the way, are rather expensive. All of these are going to be expensive, but those are particularly expensive. But there's a couple other options. Depending on the way in which you remove that electron, you might not just remove an electron and leave everything intact. You can easily fragmentate your molecule. You can shatter it into lots of little pieces. And so now instead of getting one signal at the back end of saying, here's your molecular weight, it'll be, okay, here's a whole bunch of molecular weights. The highest one is presumably your molecule that just lost an electron, but all the other ones were its fragments. Well, depending on what your molecule is, depends on what fragments will be broken up into. And that way we can do a couple things. One, we can try and like, okay, this fragment looks like a CH3 group, so we got a CH3 group on there, and this fragment looks like that. Or, what's more commonly done is, okay, we've got a bunch of patterns here. Let's match this up just like we would a fingerprint. Have the computer go, hey, computer, what matches this spectrum, this blend of masses that came off of this molecule? And the computer's like, here's your top 10 choices. This is the best one. And of course, with computers, it basically is just click a button and it gives you this. If you watch NCIS or a lot of the forensic shows, this one makes a major debut. This would be Abby's major mass spec. Now, I will be blunt. They take a bit of liberties. They're not that impressive. Nothing is as impressive as is on TV. But this is the basic idea. And of course, with mass spec, you can do a couple things. You can stick it on the end of a gas chromatograph. That way you get GC mass spec, so you separate out your chemicals, so the poor mass spec isn't trying to deal with a mixture. And you know basically what it is, but you also know where it retained on your column, so you have more information about your chemical to get a better idea of what that is. And that will really tell you a lot about your mixtures. And that's a very common approach to analyze substances. If they're volatile enough that you can run through gas chromatography, and then you send it through a mass spec, boom, you know exactly what you've got, you know how much you have. The mass spec isn't great on that, but the gas chromatography is. You run it through gas chromatography, the mass spec tells you, hey, what you got? So you now know your blend, and it's a great approach. You could also do this with liquid chromatography if you would prefer. It doesn't have to be a gas, so if it doesn't vaporize well, you could run a liquid chromatography and stick that onto a mass spec. You wouldn't send the whole thing through, but you know, you'd send a little bit into the mass spec, and it tells you what your mixture is made out of. Absolutely wonderful technique, dominates the chemistry in trying to figure out what things are, and because it's a great technique. So with that said, those are a few different ways that we can use light or other types of spectrum in order to figure out what's in our mixtures or what our substance is. And so with that said, have a wonderful day, and I'll see you in later videos.